Let's look here again, this time with weak acids. This is an overview, and it's not going to make any sense to you unless you've gone over the outline and done the web assigns. So this sort of like, I hope will bring a lot of things together for you. Now, weak acids, there's a lot more weak acids in there than strong acids. And the most common weak acids are ones that are organic acids, where you've got an organic compound and then this H+, which sticks pretty well to this. A second way of showing an organic acid, rather than this ionic one where we have an H+ and the acetate ion, is to show sort of its structure, where you indicate that the acid part of an organic compound is really a double bond oxygen, single bond oxygen, and H. And this little H is what's going to end up ionizing to some extent. Knowing the organic structure a bit makes seeing them a little bit easier. So if you see either form, and both forms have been used on the exam, especially this one that shows a double bond oxygen, OH, makes things a little bit easier. But still, these are H and A, but the HA sticks together pretty well. Now, another form that you're going to see occasionally is where you have a cation that has an extra hydrogen on it. In this case, the ammonium ion. And it has this chloride, but this chloride, because it belonged originally to a strong acid, is a spectator. So don't worry about that chloride at all. You can just sort of almost erase it and just think of the ammonium ion here as being the HA, where you've got a little hydrogen on there that's come off. You're going to start off with a positive charge, but again, you can end up handling that. Now, the thing is, the particulate drawing of these, most of the molecules are going to stay molecules. You can just stay HA, and only very few of them, in fact, this would be an exaggeration, will actually, let me draw this in, ionize. So we're going to have, in fact, this is an exaggeration, because this is going to be 1 out of 5 of them ionizing, when actually it's probably going to be more out of 1 out of 100, which would be a tough drawing to make. So weak acids are really mostly the molecular form of the acid, and then some of these characters will ionize. So let's go to here we go, second page here. Right here, we've got the ideal model of a weak acid ionizing. Now notice I've got the double arrow rather than the straightforward arrow from a strong acid. And these H+ concentrations are going to be low, and of course the A-. Now this A-, and it's worth remembering, is the conjugate base of this acid. And one of the things about this A- is that it wants to stick, I'm using that, it will end up sticking to the H+ to turn back into this molecule. So it's an active participant. It's no longer a spectator ion. When you write a net ionic equation, you have to show the weak acid starting off this way. You don't show it ionized. So the weak acid, because it is mostly unionized, is written in a net ionic equation as HA, very different than the strong acids. Let's now look at an ice chart. And ice charts are really, really useful for our weak acids. I've made one up here where we have 2/10 molar strong acid. We're putting it in water. We're assuming that there are none of these ions floating around. There are a few little H+ ions from the water, but we're going to ignore that. As I said, only a small amount of this HA is going to ionize. So we started with 2/10 molar, and we're going to have pretty much 2/10 molar. You're not going to notice the difference much. I mean, you might think about it possibly being there, but subtracting 1,000th from 200ths is not going to make much of a difference. But we are interested in H+. I mean, we are interested in acid concentrations of things, because even low acid concentrations can be significant in chemical reactions. So we're going to add both H plus 1,000th molar and A minus 1,000th molar. The Ka, the equilibrium expression, is going to be tied together with these values. Now, you don't have that many things to deal with. You only have to deal with what's referred to as the constant, and that's not going to change, and these concentrations. Fortunately, the HA is usually given to you. They say, okay, we made this acid up to this concentration, and it's not going to change much from that. So I'm going to take these equilibria values and put them right in here, and fortunately, the H plus and A minus are the same. We can square that, and we come up with a final value for the constant for this acid is 5 times 10 to the negative 6. Now let's be a bit cautious here. You should have a good feeling about logarithms and the Ka's, because you'll want to change the Ka into a pKa. It's done routinely. Now, like I said, this value is 5 times 10 to the negative 6. So it's between 1 times 10 to the negative 6 and 10 times 10 to the negative 6. If it were just 1 times 10 to the negative 6, it would have a pKa of 6. It's not as strong of an acid. If it were all the way up to 10 times 10 to the negative 6, it would have a pKa of 5. So when you see 5 times 10 to the negative 6, you should realize it's going to end up being a little bit less than 6 in terms of a pKa. And if you actually did it with a calculator, you get 5.3. The reason I wanted to go over this is because very often these problems will be on the multiple choice part of the exam, and you have to be really, really comfortable with dealing with the negative logs. So let's go to the next page. Less than the pH. Let me go back to forward. That was less than the pH that we had here, which was 3 for the 2/10 molar acid. All right, that's and look at another possible problem that you'll have with weak acids. Here we go. We're starting now, instead of with 2/10 molar, 2 molar. And now I'm saying, you have the Ka. We just figured that out. Here's the Ka. Now I want to know, what's the pH of the solution when we make the acid all the way up to 2 molar? Well, that's where our little x's come in. You should be comfortable with that. One of our redeeming features of weak acids is that the initial concentrations will be pretty much the same as the equilibrium concentration. So we can put that right into our expression. And it's nice, we've got a squared here, and you could solve for this, but because this type of problem is so common, it's probably a good idea to memorize this expression that you can use to quickly, and you've got to do that on an exam. You've got a limited amount of time. I wish we had more time for the exams, but they're pretty long as they are. Remember this one. If you have a weak acid and you know its Ka and its concentration, you can find the hydrogen ion concentration immediately by taking the square root of the concentration times the ionization constant. Having to go through the entire equilibrium expression is going to be tough if you're pressed for time. So this is a shortcut that's really, really worth knowing. And again, here I am going through it completely and solving for the concentration of the hydrogen ion. I rounded it off here because I was pretending I was working on a multiple choice test, and I multiplied the 5 times 10 to the negative 6 times 2, the Ka of the acid times its concentration, rounded it off to 10 times 10 to the negative 6, and the square root of 10 is going to be close to 3. So I know that the hydrogen ion concentration is going to be about 3 times 10 to the negative 3. You've got to do a little bit of rounding, when you're using the multiple choice aspect because you're missing your calculator. And again, you can look, it's going to be a value in between both of these, in between a pH of 3 and a pH of 2. And if you had your calculator, you'd see the pH is 2.5. That was much it in terms of our weak acids.